time to get going. New chapter. We're going to start looking at spacecraft relative motion. We start today, and then we'll talk about some maneuvers, including what we call rendezvous, which is a French word for meeting up. So we're talking about satellites that fly pretty close to each other. So two orbits are involved now, one of what we call the chief and the other one is the deputy. And we want to find a way to represent how these objects move with respect to each other, assuming, again, they remain close to each other. Now, close to each other is all relative. If your orbit is LEO and the radius is 7,000 kilometers, a few kilometers of distance is probably close to each other. If your orbit is GEO and your radius is 42,000 kilometers, maybe you can push it a little more. It's all relative, right? We'll talk about linearization as well today. So when you linearize the equations and you work in the vicinity of a linearization point, how good is that linearization? It depends on what kind of problem you're representing and how bad of an approximation you can live with, okay? But why do we care about this? Well, because we are doing it every so many weeks, bringing stuff to the International Space Station. That's what you do. You have a spacecraft in orbit and another one that is coming close up to the point of actually docking. But before I dig into so what we'll actually end up doing is finding the equations of relative motion that are called, in literature, Cloyce-Wiltshire equations. Actually, there's two names for these, because they were found independently in different decades by different people for different problems. But Cloyce-Wiltshire or Hill equations, they are linear time invariant equations that represent how two spacecraft move with respect to each other when they're close. Why do we care about linear equations? Because the theory for linear systems and their control is very well known. And when you have a problem in your hands and you can linearize it and it works pretty well, you really should do it, because we're engineers and we can devise solutions, analytical solutions, and control strategies pretty easily when things are linear. So, but before we even get to this, I don't know if I'll have the time to actually find the equations entirely, probably. I need to refresh a couple of concepts. The first one is, because we use it at least next time, it's state space representation. Familiar with this? You should be. Yes? No? Maybe? So, this is a way to compact differential equations so that you can handle them, especially for the linear case, in a very convenient manner with matrices and vectors. So I'm actually going to start from these equations. I'm going to write them there, even though we haven't derived them yet, just as an example, and see how you put them in a state space form. So example, for now these equations are just given. I have three variables and three differential equations that look like this. Omega squared x equals 0. Then I have y double dot plus 2 omega x dot equals 0. And then I have z double dot plus omega squared z equals 0, where as far as I'm concerned for now, omega is just a constant, okay? So these are homogeneous. There is no input on this side. There is no forcing. Think about this as, your typical problem that you see at the beginning of an engineering course. The spring problem, maybe with some damping. Of course, this is not that problem, but it's a bunch of differential equations with no input. And then you study the case when there is input. But for now, we don't have it. For now, this is just three differential equations that are second order, because I see time derivatives up to second. They are linear, right? Because the x, the y, the z, and their time derivatives do not appear in cosines or divides or anything else. They're all linear. And they're also time invariant. Because the coefficients in front of the variables and their time derivatives are constant. They don't change with time. I don't see an explicit dependence in time there anywhere, right? Which is also called, in literature, LTI. It's a linear time invariant system. Second order differential equations, LTI. These, you know this is decoupled, right, from the other two. You can actually solve this one by itself. That's actually an oscillator. You should recognize that. It's an harmonic oscillator, right? Second time derivatives, an omega squared, and x. This is just a z, but doesn't change the fact that that's what it is. So this is decoupled from these two. You can look at this equation by itself. These ones are not, because the x is here in the second equation, the y is here in the first equation, so you cannot solve any of the two without solving the other ones. That's fine. So, but people don't like to have systems of differential equations in this form. This is not state space. This is just the equations the way they are. And so to obtain the state space representation of this, if I'm just wasting your time because you know how to do it, just let me know. Am I wasting your time? No. OK, cool. The state space representation is based on the idea that I don't want to see second time derivatives here. And so I'm going to perform a change of variable by, say, let's define the state vector big X, capital X, which has 6 components. I'm going to define what they are in a second. X1 through 6. These are what? They are the variables themselves, x, y, and z. And you start putting after those the time derivatives, and you stop at n minus 1, where n would be the order of these differential equations. The order is 2. I see the highest time derivative is second, so I stop at the first one. If I had x triple dot here, I will have to add the x double dot, y double dot, z double dot, etc. Okay? You stop at the n minus 1 derivative. What does this allow me to do? Well, if I substitute these variables in there, my equations become what? Let's see. What is x double dot? X dot is x4. So I can say that x double dot is also x4 dot, right? That is correct with my change of variable. And then what is y dot? Y dot is right here is x5. And then I have a minus 3 omega squared x. And x is just simply x1. And that is how my first equation looks like. And then y double dot is going to be x5 dot, because x5 is y dot. And then I have 2 omega x dot, which is x4, equals 0. Last one is x6 dot plus omega squared x3 equals 0. So this change of variable made all the double dots disappear. I don't have any second order time derivatives just because I changed the variables. And so from here I can do this. If you allow me, I'm actually going to do something on these equations directly. The next step is I'm going to take these equations, and everything that doesn't have a time derivative goes to the right of the equal, which means, if you allow me to do it, this becomes a plus, this becomes a plus, okay? Equals, plus, this is gone, this becomes a minus, right? Have I forgotten a square somewhere? No. And this becomes another minus. Make sense? So that's the next step. First, you make the double dots disappear. Then everything that is a time derivative goes on the left. Everything else goes on the right, which allows me to write the system the following way. What if I put here my x, big X dot vector, which will look like this? I can say that this is equal to a matrix that I need to populate times the vector x itself. Okay? So in other words, what I'm trying to write is that same system in this form. X double dot equals AX. This will be your state space representation of the system that uses the state vector, which I have defined that way. State vector is the variables, time derivatives until n minus 1, then you stop. and you rewrite the system the following way. So I just look at those equations and I start populating the matrix. What is x1 dot? It's x dot, right? And so if I have to map it into this vector here, is which of these variables? It's a fourth, right? So basically I have 0, 0, 0, 1, 0, 0. The same goes with a shifting position for the second one, which is y dot. And then the third one, so this should be actually at the level of x2 dot, just to make it look like it's actually there. Okay, third one will have the 1 at the end, and that's the first three. And then the last three are actually my equations, the ones I gave you. So can barely see from here. Let's see, x4 dot is a 2 omega x5, right? Or well, actually there is a 3 omega squared on x1. So here I'm going to have a 3 omega squared, then 2, 3, 4, and a 2 omega on x5, and then 0, right? x5 dot is minus 2 omega on x4 only. 0, 0, 0, minus 2 omega, 0, 0. And the last one is minus omega squared on x3, 0, 0, minus omega squared, 0, 0, 0. This is your A matrix. Okay? That's the procedure. Given a system, and this applies actually for nonlinear systems too. I've done it for the example which is of our interest, which is a system of linear equations. But the same is valid for something that had sines, cosines, basically nonlinear equations. You will still do the same. Define the state vector the way I've done it, up to the n-1th derivative, time derivative. Bring everything that is not a time derivative after the substitution on the right, and assemble your, well, in that case, will be functions, but the idea is the same. Make sense? So this is how you do state space. And these equations that we're going to derive are very often seen this way because we can use this matrix A in a lot of different ways. When you have a linear system, you can do a lot of stuff. Okay, well, there is a little bit more to say. I said that those equations don't have any input for now. Well, the most general representation of a system, a linear system, which may be controlled, meaning there may be an input from outside, is the following. It's still there, x dot equals ax. Now we have a bu, where u may be an input, a control variable. So u may be a vector that is of dimension m, where remember the state vector is of dimension n. I have n variable. Sorry, I don't know why I'm writing everything so small. Let me do it again. X is n. U may be a different dimension. Maybe m as in mother, that's n as in Nancy up there. Number of control variables. And B will have to be another matrix, which has to be what dimension? It's an n by m matrix, right? This is a vector of n components. The A matrix is obviously n by n, all right? Because it's mapping x dot with x. They have the same dimension. This must be a square matrix of dimension n. Depending on how many control variables I have, which is just a generic m, then B has to map this u into n equations. So it needs to be n by m. Bless you. So we're not done. So this would be, again, go with your mind, go to examples like these may be the parallel of an harmonic oscillator, whatever system you have that is left alone to do whatever it wants to do from an initial condition. You don't give it any input, but this is now the forcing part. You may actually want to give it an input, okay? So that's what you would do with state space representation. You just have multiple inputs. They may be coming in. Also, we are often able to write equations in terms of certain variables, but that doesn't mean that we can measure all those variables, right? The fact that I'm writing equations for a system, this is dynamics of a system, for example. The fact that I'm using a bunch of variables to represent how the system evolves in time, it doesn't mean that in practice I have sensors to measure all those variables, right? Not a guarantee. So usually the output, I'm just covering general linear dynamics here. The output y, the vector y, may be not the entire state vector x. It may actually have a component that is affected directly by the input. In most of the cases, this doesn't exist, but it may be there. If you can measure the entire state vector, then this is an identity matrix. Otherwise, it's just a matrix with a bunch of numbers that maybe some of them may be zeros or not. But this is just refreshing state space representation. This is how you put your system in state space representation. You may have an input. You may not be able to measure everything in the state. Depends. If I have a spacecraft that it's changing orientation, actually let's put it this way. If I have a spacecraft below the GPS constellation, nowadays spacecraft can carry a GPS receiver, so they can know their position like more or less the same way you do it here. But that is what it's measured. You can say that the x, y, and z are measured. The velocity is not usually directly measured. It's derived from measurements with some Kalman filters or other procedures, but you don't measure that quantity directly. Okay? So what I'm saying is that these would be what you can measure. This is what people do when they talk about state space. They find out what are the variables that they can measure. Is this clear? Nothing new. Shouldn't be really that new. Well, the second piece of the equation that I need is linearization, because again, we are engineers and we like linear stuff. Now, if I have a system of differential equations that are not linear, you can still put it in state space form and it will look more or less the same. Say that I have n variables again, x1 through n. The difference is that now you will have functions, okay? So this is x1 that goes to xn, then I may have an input, m different inputs. These could be dependent on time, but the idea is the same. You boil down to first order differential equations after you do your change of variables, except on the right hand side now you don't have all nice constants times the variables. You may have complicated nonlinear expressions, but still this is how you would put it. So in a state space form, this will look like the big X state vector dot is equal to a big function f, which is actually a bunch of different functions, f1 through n, of x itself, the vector u, and maybe time. And when you have nonlinear systems, unfortunately, well, there is theory for them, but it's much more complicated and not that general as for linear ones. But we may be interested in looking at what happens in the vicinity of a point. Let me actually draw something here that I don't want to erase for the rest of the lecture, hopefully. So say that you don't really care about what happens for the entire range that x1, x2, etc., xn can span. You don't really care about what happens in the entire space that that state vector can span. You really care about what happens in the vicinity of a certain particular x0 and a certain particular u0. So this is a particular combination of x1 through n, and this is a particular combination of controls that you pick. That's your reference, right? You want to linearize about that. How do we do that? We'll see in a second. But the case that we want to explore is this one. Now I have my planet. I don't know what this is, some continent here. And I am looking at one spacecraft that I'm going to call the chief. You find it in literature called the chief or the target spacecraft. There's a lot of different terms that are used. And its position is given by the vector RC. And this may be the International Space Station that is just going around by itself, with a bunch of astronauts inside, on a kind of a circular orbit. And then there is a refueling spacecraft launched from KSC that it's coming close. And we're going to call this D, the deputy, or also called the chaser. So the nomenclature is, again, people say chief and deputy, or target and chaser, because usually that is the one that it's maneuvering to reach this guy. It's just nomenclature again. And so in that case, the position vector, we're going to call it RD, right? So this is RC up here, and this is R of the deputy here, RD. And let's call this little vector that is the difference between the two, let's just call it rho. Okay? So one problem, which is exactly what we're going to face, maybe I want to know how the deputy is moving with respect to the chief, but I know that they are very close. They're not going to go away from each other. They're a few kilometers at the most from each other, maybe a couple of 100 meters. So I really don't want to explore the full-blown nonlinear equations of motion for this guy and for this guy. I actually want to linearize the dynamics of the deputy with respect to the chief. That could be a problem where you have equations that are nonlinear and you want to linearize them, which I will do today. Why? Because again, if I can put the evolution of this vector in some kind of state space form that looks like this, well, this actually has an analytical solution. You can integrate those equations numerically or not. It's analytical. You can, as we will do, derive impulsive maneuvers that go from where you are exactly to the chief analytically without doing any numerical iteration. Even continuous control, when you have a thruster that turns on and stays on for a while, can be solved kind of easily. When things are linear, they can be manipulated pretty well. So that's why people do it, and that is what you have in reality. You don't have these objects being too far away. Once you've done your Hohmann transfers, your bielliptic transfers, you're not going to be exactly at the other object's location. You're going to be close. And that's when you can have these equations that we're going to derive kicking in and designing control strategies based on those equations. But how do you linearize a system like that? Well, again, say that I care about x0 and u0. Well, that is my linearization point. If this is my reference point, and in that case, what do you think the x0 would be? What is the reference with respect to which you're going to linearize? Is the chief. The chief is flying around, so it can be an evolving state. But if you assume, as we'll do, it's in a circular orbit, that can be your reference. So in general, if I have that as my reference, x0, I can say that any other location for the state vector x is x0 plus some delta x0, which of course has to be small enough so that the linearization holds. What does that mean? It depends on the problem. It depends on how much error you can afford. And the same for u. It's u0 plus some delta of u0. So I really want to find the equations based on these two guys, the perturbations with respect to the linearization point. How do you do that? Well, series expansion, right? No surprise. X dot, so this equation up here becomes, if I use this substitution here, becomes x dot 0 plus delta x dot 0. And this is almost equal to, if I linearize this big function here, is going to be what? The function computed at the linearization point, right? Plus, this is called the Jacobian of f computed at the linearization point. Seen this before? I hope. Delta x 0 plus the Jacobian of f with respect to u now at the linearization point that is multiplying delta u0. This Jacobian is really not something to be scared of. It's just a bunch of partial derivatives. If my f is a bunch of functions, f1 through fn, the df, partial of f with respect to the vector x, is a matrix made of df1, dx1, all the way to df1, dxn, and then down here you go to dfn, to dx1, dfn, dxn. So you compute all these partials. There's something similar for df with respect to u. And you compute this. So these will be functions as well, right? Sines, cosines, depends on your problem. And you take and substitute x0 and u0. Everywhere you see an x, everywhere you see a u, you substitute the value of your linearization point. And so what that becomes is, well, first of all, these are the same, right? These two guys. See that? That is my original equation. X dot is equal to f in x, u, and t. So x dot 0 is going to be equal to fx in 0, u, 0, t. So these two can be just removed. You're left with what? You're left with delta x0 dot is equal to this ugly matrix that you have to compute, which is computed though at a specific point, so it becomes a constant, a matrix of constants, delta x0 plus another matrix of constants, delta u0. And this is your linearized system about x0, u0. So if you have a nonlinear system of differential equations and you want to linearize and get something you can handle the same way you do with linear systems, you compute the Jacobians of the functions, these partials, with respect to the x's and the u's, substitute the values that are of interest, and then what they give you is, again, a and b. So these will look like x dot equals ax plus du. Make sense? Does it make sense? I'm going to do it for this particular problem. I'm just refreshing what linearization means. If this doesn't make sense in the vector form, just go to the basics. How do you linearize this? How about we just do it in a variable? How do you linearize this? About x0 equals 0. What do you do? F of x, and here I'm retaining, of course, only first order terms because I'm linearizing. If I wanted to keep more terms, I could have here the second order, the second partial of f with respect to x, etc., etc. You can have the additional terms. But when you linearize, you don't. You stop at the first one, at the first derivatives. So what do? F of x is almost equal, it's approximated by what? By f at 0 plus, what is the partial of this with respect to x? Is minus sine of x, right? That has to be computed at x0 times x minus x0, which is 0. So if I do this, what is f in 0? What? 1. What is sine at 0? Done. That's my linearization of the cosine. That's what you do when you say the angle is small. What is the cosine of the angle? 1. Do this for the sine. Swap the function with sine. You would get that the, oh, let's do it. I just want people to understand that this is just extending to more variables, but it's the same idea. F of x is sine of x now, and I have still the linearization point that is 0. So I'm going to say that f of x is almost equal to what? To f in 0 plus cosine this time of x that has to be computed at that point times x minus x0. So in other words, what is the function at 0? It's 0. What is the cosine of x at 0? It's a 1. And so here I am left with x minus 0. So this is x. That's what you do. When you say the angle is small, I'm going to replace it with the angle itself, the sine of the angle. I'm going to replace it with the angle itself. That's what you mean, right? You linearized. And so that's what we do. We don't go too far away between the spacecraft, so hopefully we can linearize. Can I erase this? Well, maybe not. Maybe I'll use this one. Okay, let's start digging into the equations of motion of the deputy with respect to the chief. I'm going to use, what kind of basis do you want to use? If you want to look at the deputy moving with respect to the chief, and you know it's going to be close to it, it's not going to fly away, hopefully, what kind of basis makes sense to use? I am an astronaut sitting on the chief, which is the International Space Station. What do you want to use to say, oh, that's the cargo that it's coming to us to give us food? What do you want to use? Do you want to use the ECI?
LVLH.
The LVLH, right? That makes a lot of sense. And so the LVLH had the R in this direction. Let me just use I. It's the X direction, right? And then he had the, I don't know how to do something that comes out of the board. Let's just say that this is the W, normal to the plane, right? Let's just call this K. And then the cross product of the two had to be somewhere in the direction of motion. This is J. So in other words, the LVLH had, let's see, it's the radius of the chief normalized Then the k is the angular momentum of the sheaf normalized. And just refreshing what we had done last time. And j is k crossed with I, right? So I'm going to use that basis to project vectors. Why not? What I'm going to do is write the equation of motion of this object in LVLH. All the vectors will be projected there. And then I'll linearize that equation of motion with respect to the sheaf. The fact that I'm using something which is a frame that is obviously not inertial makes me expect that I'm going to use something we have seen at the very beginning of the class. What is it? Transport theorem. There's no escape. Okay, so the position of the deputy is the position of the sheaf plus the little vector rho. Obviously, the little vector rho is what I hope to be able to represent with these linear equations that I'm going to find. Because this little vector rho will be expressed as xi plus yj plus zk, right? So I'm going to find equations, the ones that I actually gave you at the beginning as an example, equations that tell me how x, y, and z evolve with time. That's my goal, right? So I know how the deputy is moving with respect to the sheaf. Okay, let's use that basis. How does this look like? It's going to be RC plus x in the I direction plus y in the j direction plus z in the k direction. Do we all agree with this? Since the I direction of LVLH is defined as a line with RC, the vector RC cannot have any component on j and k, right? So that's my RC, R deputy, I'm sorry. Now, what do you need to do when you finding the equation? Of course, you've all taken dynamics. What are the steps you go through when you find the equations of motion of something? You start from its position vector, you take its first time derivative, that's the velocity, you take the second time derivative, that's the acceleration. You have to do it in an inertial basis, which is, let's call this n, which is actually ECI, right? Why? Because F equals ma is only valid if a is computed by an inertial observer. So I'm going to take the rate of change of that vector twice, which requires the transport theorem because it's not expressed in a basis that is inertial. Okay, so no big deal. What is RD dot? Which, in other words, is the rate of change of RD with respect to n. Well, according to the transport theorem, is the rate of change of the same vector with respect to LVLH plus the angular velocity of LVLH with respect to n, which is crossing the vector itself. Now, if I do this, I get, well, the rate of change with respect to LVLH is just that, just looking at the coefficients, RC dot plus X dot I plus Y dot J plus Z dot K. What is the angular velocity of LVLH with respect to an inertial basis, inertial reference frame, sorry. What do you think that is? True anomaly dot, it's a vector. What else? I'm only looking at how this basis here that is flying with the sheaf, whose position is represented by, as you said, the true anomaly with respect to some line of ups that we have defined. I want to represent how this basis is rotating with respect to this one, to ECI, right? This is ECI. And this is LVLH. I agree it's a theta dot should probably be there, but to make it a vector, you need to give me something more. It's not just a scalar. About which axis is theta dot? It's k. Don't make your life very difficult. If you have a basis where you can clearly see the rotation expressed as a single axis rotation, do that. Go for it. You don't have to do things very complicated. Of course, if you want to transform this vector, so this vector is the angular velocity of LVLH with respect to n. If you don't like it expressed in LVLH, and I I wouldn't see why not, because everything here is expressed in that basis. But if you want to go to the basis in ECI, well, then you will have to transform that vector back into the ECI basis. Good luck with that. There is the 313 rotation plus the theta rotation. You can do it, but let's make your life very difficult. You do have already a basis where you can see that the angular velocity is theta dot k. Make sense? No? You can tell me if it doesn't make sense? It's not so immediate. Yes?
Spacecraft rotating around.
Yeah, the spacecraft for now, for everything that we have done, is just a point mass. But I'm creating this imaginary object that has the center on the spacecraft, and it's, one direction is looking always in the radial direction, one is normal to the orbit, and it goes around. Yes, it moves with us, it rotates, and the rotation is dictated by the true anomaly. Make sense? So if you want to look at the orbit from above, and this is your line of ups, and this is your focus here, and you are somewhere here, this is your I-axis, right? The K is coming out, and this is your, yes, this is your J-axis. But really, all is changing is the orientation of these two guys. The axis that is pointing at you, if it's Keplerian, which is what I'm going to assume here, if everything is Keplerian, that axis just remains pointing at you. Only directions that are changing are I and J, and the only angle you need to represent how they rotate is theta. Okay? So what do I do with this? I have to cross this with that. So, yeah, cross RC plus XI. I don't think I'm going to finish this today. But that's okay. Okay. You want me to do it? Yes? No? We'll do the first one, then the acceleration. I'll just give it to you. So this first part is what it is, plus, you know what? I'm going to try to skip steps. How about that? Okay. I see a K crossed with I, a K crossed with J, a K crossed with K. I don't even bother about it. So K crossed with I is going to give me probably a J, right? So where do I see a J? Right here. So I'm going to have a Y double dot that was already there, plus, I want to say that I have it here. Don't want to make mistakes and waste time. Oh, what did I say? This one, right? K crossed with I, yes. I see a theta dot RC plus X on J. I'm just trying to collect all the terms. Okay? This was already on J. K crossed with I gives me a J. Fine. The last one gives me a 0, so the Z dot K is going to remain as it is. Really doesn't change anything. Now I have the additional term here. I had already RC dot plus X dot. What is K cross with J? Negative I agree. And what does that give me? It's a theta dot I, and that's it. Okay. That's what you have. So that's your velocity, right, of the deputy. Again, this is RD dot. That's not enough. You have to do it again. And this is where I'm going to give you what happens, because it's basically doing this one more time. I want the RD double dot, and again, we have agreed that the dots mean derivatives in ECI or in the inertial base frame. So ddt in n of what? RD dot. Well, it's the same story. You take that vector down here, you take its time derivative with respect to LDLH, which means you only derivate these terms, and then you add the cross product between omega and the vector itself. In other words, you do this. This is an LVLH, which means your I, J, and K are assumed to be not changing. But then since they are actually changing, you add this additional piece. And this is a little bit of calculation, which is going to give you this. Invite you to do it. It's really not a big deal. RC double dot plus X double dot minus theta double dot Y minus 2 theta dot Y dot minus theta dot squared RC plus X on I. Then on J you have Y double dot plus 2 theta dot X dot plus RC dot minus theta dot squared Y plus theta double dot, RC plus X on J, and then the one we like the most, which is just Z double dot. That is my acceleration of the deputy. I have just used a different basis to express it. Now I made no assumptions here up to this point, but what we actually do is we start simplifying our life because we're engineers. And the ISS is that, if that's really the example we're thinking about, and many of the spacecraft in LEO are in circular orbit. So what about if a chief is in circular orbit? What happens? What can you do? What can you do? What can you tell me about all this bunch of variables that I have there, time derivatives? There's a lot of stuff going on. This is only the acceleration. I haven't introduced any forces yet. What happens to those expressions? What goes to zero? Not everything, I hope. Otherwise, I'm not going to find any equations. What is zero? If my chief is in circular orbit, does the radius change? So this is zero, as well as this, right? Okay. If my chief is in circular orbit, what happens to the true anomaly? The angular velocity on a circular orbit is constant. So the theta dot, let's just call it omega, the same omega that I used at the beginning with those equations I gave you, and it's a constant. So the theta double dot is also zero. So with all this in mind, those equations simplify into x double dot minus 2, where you see omega dot, you just plug in an omega. Theta dot. C plus x. This is on the I direction. And then the second one becomes y double dot plus 2 omega x dot minus omega squared I y on the j plus z double dot k. And that's good. So this is equal to what? This is my acceleration. If I have a Keplerian orbit, this is equal to minus mu radius of the deputy cubed times radius of the deputy. Right? I mean, all this painful stuff is to go down to this again. It is just that I have used a basis that is non-inertial because it is convenient, believe me. It's very convenient. But that's what I'm writing. This equality here, this vector up here, it's nothing else than RD double dot simplified with the assumption on the chief's orbit, and that's what you're looking at. Okay. Still have a few minutes. Well, everything is expressed on the left in terms of the basis that we used. Let's do the same here. I don't need this. Okay. What is that? That is minus mu over RD cubed. You can see it this way. It's once again RC plus X in one direction, Y and Z in the other two directions. That's what it is, right? So these equations that I have, they are differential equations, right? The left-hand side, this is the left-hand side of this vector equation. The left-hand side has X, Y, Z, time derivatives. Do you see anything nonlinear here? I don't see anything nonlinear. The omega is constant, the RC is constant. I don't see any expressions that are nonlinear, so we're good here. This is linear. The right-hand side, if I look at this is not linear, because RD is what? RD is, it's the square root, and that is already nonlinear. RC plus X squared plus Y squared plus Z squared, okay? So if you want to start from this, which is what we're going to do, and linearize about the chief, which we have to define what it means actually, I have to basically take care of this piece here. This has to be linearized. It's the only part that is nonlinear. And that's what we want to do. And I'm going to do it for the first equation because the other ones are pretty much identical procedure. So I'm going to take that and basically take care of this piece here and try to linearize it, because the left-hand side, it's fine. What is my linearization point? If I said that the chief is a circular orbit, and that's my point of reference, what is my linearization point? I'm going to back up even more. What are the variables here? Right? Those are the three variables. Okay, fine. Because I want to really be able to come down to this and say this is the vector at this time and this is going to be the vector in 10 minutes, etc., etc. That's what I want. So these are my three variables. Okay, if I need to linearize and the point of linearization is the chief, what is x0? What is y0 and what is z0? This is important, otherwise you don't even start linearizing anything. I agree with these ones. First one is 0 as well, right? It's, again, this is the motion of this object with respect to this one. If my reference point is the chief, it means that my reference is at the chief. And when I am at the chief in LVLH, I am 0, 0, 0. Make sense? So this is important. You need to know what values you're going to introduce into the partial derivatives that you're going to compute. And well, I still have 3 minutes. You know, I'm going to start it and we'll finish it next time. So we agree we have to manipulate that expression, take some partial derivatives, substitute everywhere you see x, y, and z, substitute the zeros where needed, and that will give you the linear equations. So I'm going to start writing these. Let's see. RD, I already have it there, right? It's that square root, which is also equivalent to, let's see, RC squared plus x squared plus 2, RCx plus y squared plus z squared, which for convenience I'm going to write like this, collect the RC outside. Let's see, I have 1 plus 2x over RC plus x squared plus y squared plus z squared over RC squared. I like it that way. So if I am looking at the first equation here, this component, the I component, I have to linearize something that looks like this. Forget the minus and the mu, they don't really matter. We'll put them back when needed. So I basically have to take care of a function that looks like this. Let's see, RC, remember that's cubed. And down here I have 1 plus 2x over RC plus x squared, y squared, z squared over RC squared. Everything, it's cubed. So this is a square root. This is 3 over 2. That's the power that we have down there. This is my f. This is my function of x, y, and z for the first equation. Remember when I said before, you know, state space representation, if the system is nonlinear, instead of having a bunch of linear equations, you have a bunch of nonlinear functions. This is my f1. It's the one on the first, in the first direction. So I want to linearize this. Except the minus mu, I have to remember to put it back there. It's 49, so I'm sorry, this is an x. I'm going to stop in a few seconds, but what do you do now? This is your function of x, y, and z. you say that it's approximated by the function computed at the linearization point. So bunch of zeros where you see x, y, and z. Take its partial with respect to x. Whatever you get, substitute x, y, and z being 0. That is multiplying the x, and that's how you get your equation, which we will do next time. But start doing it. It's really not that big of a deal. It's a couple of lines of calculations. Bye, thanks.